Alright, so welcome back to the third and final part of the Thevenin video series. So far we talked about the fact that a real voltage source has its own internal resistance, its output impedance as it's called. Furthermore, any complicated system of resistors and linear elements can be replaced by a real voltage source if we look at it between two terminals. So again, I have some circuit here. If I just put wires out between 2 points on that circuit, I can plug in a load resistor or anything I want between these 2 points, and the rest of the circuit is just going to look like a single source and a resistance. And that's the idea of the Thevenin equivalent circuits. In the second part of the video, we talked about how to calculate that. And in this third video, we're going to put our money where our mouth is and do a quick example of how to get the Thevenin voltage and resistance of a given circuit. So I just was digging around for an example and scribbled one down that would work out. Let's talk about a double voltage divider. A double voltage divider. So we've done a voltage divider before. Let's do a double voltage divider, which is twice as good. So we'll do something like this. Keep the numbers fairly simple. But effectively, we have two voltage dividers, and we're going to look at our output voltage here. The output of our voltage divider, our terminals in our Thevenin equivalent circuit, are going to be here. Might as well maintain a semblance of the same color scheme. And this is going to be our load resistor here. So we're going to plug in various things. In fact, in this case, we're just going to plug in a 1K resistor here. But we might want to plug in other things. And the Thevenin approach is just going to help us calculate what our output voltage is and our output current is. What's the current across that thing? What's the voltage across it? And to solve it, or to do this, we're going to solve the Thevenin equivalent circuit. So that's going to be equal, this whole thing is going to be equivalent to some voltage source with some resistance, and these are going to be the same two nodes here, the same two nodes, A and B. And in this case, we're putting 1 kilo ohm across it, but we could put really anything across it once we've calculated this. So let's calculate our Thevenin equivalent circuit. So we're going to apply the textbook, or rather the cookbook algorithm. It's kind of just a recipe. So we're going to find V Thevenin. And to do that, remember, we just remove anything between the terminals and calculate the equivalent resistance. So let's do that. We got 30 volts. We have a 1K resistor. We have another 1K resistor. We have another 1K resistor. And when I say 1K, I just mean 1 kilo ohm. And infinite resistance between these points A and B here. And what is the voltage? The question is, what is the voltage between the points A and B here? Right? So this is going to be our Thevenin voltage. That's our Thevenin voltage between here, because it's equivalent to here with an infinite load between it, so it's going to be the same voltage all the way across here. So where is the current flowing in this circuit? And this is always the case with calculating V Thevenin and R Thevenin. You draw it and you stare at it for a second, and usually something pops out. So we can see here this is actually a much simpler circuit than it looks like at first. Because this is an open circuit on this side, how much current can flow across this resistor? None, right? There's no current flowing across it, and that means no voltage is dropped across it. So it's the same potential here as here as here. This is also V Thevenin. And this is our standard voltage divider equation, right? So that's our voltage divider equation, and we can just plug it in. We'll do it the old-fashioned way. We'll just say that we have some current here, I, and the I is equal to 30 volts, I over R, divided by a total of 2 kilo ohms. 2,000 ohms, and that's going to give me 15 milliamps. There's going to be 15 milliamps of current flowing across this resistor. And the voltage, the Thevenin voltage here, is going to be 1K, 1 kilo ohm. V Thevenin is going to be equal to 1 kilo ohm, is IR, we'll say. IR is equal to 1 kilo, no wait, that's not I, 15 milliamps times 1 kilo ohm. That's what I'm trying to say. Or 15 volts. That's our Thevenin voltage. Now, if I plug that 1K in here, that Thevenin voltage is still going to be the same. If I happen to have a 1000K or a 0K, it's also 15 volts here. So we've got our first piece of the puzzle. We have our first piece of the puzzle here. We have 15 volts. All right. Now we have to find our Thevenin. So let's have a look at our Thevenin here. I'm going to have to erase this or buy a bigger whiteboard. So, luckily we're not in class, you can just pause it. Step 2, we're going to find our Thevenin now. Now there's a few ways we can do this. We can replace this with a wire and calculate the current, and that current is V Thevenin over R Thevenin, so we could solve that way. Or we can reduce all the voltages down to 0 volts and equipotential, i.e. a wire, and find R Thevenin that way directly. Let's do it that way. So our circuit now is going to be replaced by a wire, 1K, 1 kilo ohm, another 1K, and we have point A here, and what do we got here? Just a wire that goes to B. And we want to find the resistance here, the equivalent resistance. That's going to give us our Thevenin resistance. So, applying this, let's stare at this for a second. If we look very carefully, we can see this is all one wire. So this, maybe it's easier if I draw it slightly differently. This is actually the same as our 1 kilo ohm from here, or 1K from there. I'll keep equally lazy and just write 1K. And our 1K here, 1K here, and that goes to B. If you can tilt your head right, that's the same as this circuit here, which is equal to this resistance here is just half a K, so it's 0.5K or 500 ohms, however you'd like to write it. And we also have this 1K here that goes directly to A. Okay, so we have a total of 1.5K, 1K plus this half K here. That is my Thevenin resistance. Awesome. So R, the resistance between R and A and B, we'll call it RAB, is equal to R Thevenin is equal to 1.5 kilo ohms. Great. We've just solved our final piece of this puzzle here. So this is 1.5 kilo ohms. And this is the Thevenin equivalent circuit according to these two terminals here of this whole thing here. It's a 15 volt source with a 1.5 kilo ohm output impedance. We're pretty much done. We want to find what? We want to find V out and the current through here. So let's do that. So we'll wrap it up. So now we're going to put our 1K load resistor, this guy here. And this is our circuit here. So now we have our voltage divider equation. Again, everything's a voltage divider in this course. If I want to know my output, my voltage between A and B, it's going to be, so my VAB is what I actually wanted when it's plugged into the 1K, is going to be equal to my load resistance, this is my R2, 1 kilo ohm divided by what, 1 kilo ohm plus my 1.5 kilo ohm here. All right, so that's times 15 volts. That's my voltage divider equation. Okay, so what do we get? We have 1 over 2.5 kilo ohms times 15, so let's bring the 15 up here. All right, do some quick math. Times both sides by, or top and bottom by 2, that's 30 over 5, and that's equal to 6 volts. So in this case, I'm going to get 6 volts flowing, 6 volts dropped rather across this resistor. How much current is flowing? So I'm going to say from A to B, is just going to be that 6 volts dropped through a 1K resistor. 6 volts over 1,000 ohms is 0.006 or 6 milliamps. And we're done. So we found the Thevenin equivalent circuit of this thing is a 15 volt V Thevenin and a 1.5 kilo ohm R Thevenin, and therefore we know the voltage drop across here. The beauty and the power of the Thevenin method is now we know what we'd get if we plugged a bunch of different things in here. If we had a potentiometer, what if we accidentally shorted it out, for example? What would we get? Well, if we accidentally shorted this out with a wire, let's say we accidentally short these 2 points out. Are we going to blow up our multimeter? Probably not. Let's see. We get the circuit. Here we've shorted out our circuit here, and we're going to get a total of 15 volts divided by 1.5 kilo ohms, which is 10 milliamps. If we accidentally short out our circuit, 10 milliamps. Notice that we get that just like that. We get it right away because once we've solved for the Thevenin equivalent circuit, we can plug anything in there. If I forgot to put a resistor at all, I just let that 1K hang there, I'm going to get 15 volts across here. So I'm going to get 6 volts for 1K, 15 volts if there's infinite gain, or say probably about the same if I have like a 10 mega ohm load here. And if I accidentally short it out, I'm going to get a maximum current through here of 10 milliamps. So that's Thevenin, that's Thevenin's idea, how to use it. And the key is just to do a few practice problems, but it's very important, not so much that you understand the proof of Thevenin's theorem. It's actually quite boring. You just write down a system of equations, and it's more equations than unknowns. You exploit some freedoms. It's like a mechanical proof. We won't go into it here, but effectively, it's not important to know why the theorem works, but it is important to get the intuition between how this cookbook works. Why does it work to find V Thevenin by removing the load and calculating the voltage? Well, if it's equivalent to the circuit, if that's really true, I can pull that out, and that is effectively what V Thevenin is. How does it work that I can scale all the voltages to 0? Well, that's exploiting the linearity of the equations of Ohm's law. Why does it work to short out the current and measure I is equal to V Thevenin over R Thevenin? Well, that works again because this whole circuit, whatever I put between here, these two quantities are independent of it if the Thevenin theorem is true. So that gives me I can just play with this load resistor to basically get a system of equations, get enough equations as there are unknowns, and extract V Thevenin and R Thevenin. So practice makes perfect with these equations, with this technique of Thevenin, and after a while the intuition becomes a bit more clear. Okay, so that's it for Thevenin's theorem.